Hi and welcome back to Podcast School. This is another video podcast in the series of electronic systems. Today we're going to take a look at the 555 timer in monostable mode. The 555 timer is an integrated circuit, and we spent some time looking at those in a last podcast. And they implement a variety of timing applications. The 555 was designed and invented by Hans R, and I have no idea how to pronounce this properly, Kamenzind, I think. It was designed in 1970 and introduced in 1971 by a company called Signetics, which later became Philips. I've said there that the original name was the SE555. Lots of people have asked me, why is it called the 555 timer? Where do these numbers come from? And I have to admit, I do not know. And I have asked lots of people and they don't know either. So if anybody knows the reason for that, I would love for you to comment on this podcast and tell me where that comes from. I said there that just really that they're used both in industry and in schools, and that's because they're very easy to use. They're very low price. They don't cost very much, and they're really good. They've good stability. But around 1 billion are manufactured each year. So that's a little bit of history about it. But now we need to know how they work and how we can use them. Okay. So there I've said timers, the 555 timers have a very high output current. Okay, so you can drive output devices directly from them, and they can give you accurate and repeatable time periods. Here we have a symbol which we use for the 555 timer, and just to contrast that, I've shown you the pin layout, and you can see how different the layouts are. Okay, so up here we've got pin 1 and running down, round and up, the way we usually do on an integrated circuit. But look at where they are over here. Pin 1 is down here. Then pin 2, they're all over the place. Look, pin 3, pin 4, 5, 6, 7, 8. So it doesn't run around in the anti-clockwise direction the way the pin out does. And that's basically because of its configuration and the ease of drawing it, and you'll see what I mean by that in a little second. It just so happens that the stuff on the left we normally connect to pins 7 and 2 and 6, and 3s are output, so we put it over at the right hand side. That's why. I've said there that 555 timers can function either in monostable or what's called astable mode, or astable circuits. But this requires a number of external resistors and capacitors. Today we're going to only look at the monostable mode of operation. So there is what I mean by monostable. It's a timed period, a timed pulse, where the circuit, the 555 timer should I say, raises the output to a high level and then off again for one period. Okay, so it goes on for a period and then off. I've said there that in the one stable state timer, the monostable timer always returns to the original state, and you can see that in the diagram after a time period. And here is the basic configuration. So you can see now why we put 7 and 6 and 2 down this left hand side, because that's where we're connecting to, okay? And 3 over here, that was the reason for that odd layout. 4 and 8 are normally always connected to VCC, so they're better placed at the top. And of course 1 and 5 are at the bottom connected to ground, so that's why we put those there. You can see that the configuration that we've got here, we've got basically 2, if you think of them as potential dividers. So here's one potential divider, even though it's a switch, don't worry about that. And here's the other. Okay, oops. And there's the other. Bit wonky. Don't forget, you can think of a switch as a potential divider. It really is a resistor with a very high resistance, sometimes almost infinite, and a very low resistance, sometimes almost infinitely small. Okay, so you can think of those as two potential dividers. I've said there that R1 and C1 are external components whose values fix the time t. So these two have something to do with the time t that the output's on for. Let's have a look. Okay, so that's just sort of driving home my point that this LED as the output here will come on for a time period once the switch is closed. This switch here, I mean not the one on the VCC. So this switch, when this switch is closed, or momentarily closed should I say, the LED will light for a time period. Okay, that is the overall function. That's what will happen, but we need to know just a little bit more detail than that. So let's take a look together now. I'll go through this in just a little bit more detail and explain what these components R1 and C1 are doing. Okay, so let's have a look at these external components R1 and C1 then. So I've said there that in its stable state, the trigger input is held at VCC. And remember, the trigger input is pin 2. Okay, I've shown you this here, and there it is there. Okay, there's pin 2, and that's the trigger input. I've said that the output is 0 volts and the capacitor has no charge. And the reason for that is that the current that would flow through R1, or so of course this switch is this little top switch, that's down connected so that there's power to the circuit, so that there would be normally current flowing through R1. Okay, but it's diverted into the threshold pin, pin 6. There's pin 6, there's pin 6. So normally current would flow down through and in, so that this would be seen, current flowing down through here would see 6 as being a very low impedance, and it would be very favourable for it to enter at pin 6. Therefore, there's really no reason why it should charge the capacitor at that point. Okay, and then that current it finds its way on out through the IC and down to ground. Okay, down here. That's what normally happens. But if the circuit is triggered by a negative going pulse, and remember what I mean by a negative going pulse, I mean this, okay? It's a pulse where it goes from a high and it drops to a low, okay? A negative going pulse. Obviously a positive going pulse would be that, okay? So it's triggered by this negative going pulse, and this pulse must fall to below 1/3 of VCC, okay? Now, I'm going to give you. I'm going to fill in this graph here. Watch what happens. There's the output voltage, which is at pin 3, and there's also the trigger voltage. Just watch what happens. Okay, get it? So at the time whenever there's a falling edge, or remember, falling edge is another word for a negative going pulse. A falling edge or a negative going pulse, whenever that's detected at pin 2, and remember, why would that be the case? Well, if you think of, like I said earlier, this little portion is a potential divider. Okay, it just so happens that the bottom switch is, well, if we think of it like a resistor, obviously it's got a very high resistance when the switch is open and a very low resistance when it's closed. So when it's open, it's got a very big resistance. So imagine a huge resistor in there, and you know that from the potential divider that the potential splits in accordance with the resistance. So big resistor, big voltage. Okay, but if that were to go very, very small, then of course 2 is basically connected to ground. Okay, so it falls, and that's what produces this negative going pulse, this bit. Okay, I've written all over my diagram, I'll clear it again. Okay, so momentarily closing the switch will cause this negative going pulse, and the width of that pulse will really depend upon how long the switch is pressed for. Okay, so that's the width. So whenever that happens, we can see that our output becomes a high for a predetermined period of time. Okay, so obviously it goes high for this time, and the LED, of course, will light. Now that's what happens. So let's just figure out exactly why that happens. I've said there that on triggering, the output rises sharply to VCC. We've seen that already. And current no longer flows into pin 6. So you remember just earlier I said that current flowed through R1 and out and into pin 6, and then somehow internally to the chip made its way down to ground. Okay, that no longer happens. Instead, it flows into the capacitor, gradually raising the potential difference across it. So this no longer happens when it's triggered. The current flows into the capacitor. And as you know, whenever that happens, the capacitor begins to charge. The potential difference, that's what PD is there, is sensed by pin 6. So remember, pin 6 is actually the threshold pin. And it senses voltage, that's its job. Okay, and when it reaches to 2/3 of VCC, so in this case if VCC were 9, then obviously 2/3 is 6, so whenever it reaches 6 volts, the output falls to 0 volts again. Okay, and we saw that from the graph. C is rapidly discharged again through pin 7 this time, and if you have a look, pin 7 is the discharge pin. So if you imagine the current all the electricity stored within the capacitor, suddenly whenever the output goes low, suddenly the discharge pin does its job, and it discharges the capacitor back through to ground. The IC then is now ready to be triggered again. So really all this is it's the pins on the IC that are changing their input impedance or input resistance, you can think of it as. In one state, before it was triggered, 6 is got a very low impedance and current flows directly through the IC and down to ground through 6. But when the 2 receives a negative going pulse, 6 changes its input impedance and suddenly current begins to charge the capacitor. Whenever the capacitor is 2/3 charged of the supply voltage, then the threshold pin senses that and turns off the output, and at the same time 7, the discharge pin, discharges the capacitor through the ground. Now, if you're thinking about this, therefore you can already tell me that the output, or the time when it's on, depends only on what? Yeah, the values of R1 and C1. Okay, so we can set up different output times just by changing R1 and C1. In the next slide, we'll see exactly how we do that. Okay, I'm not going to worry too much about this. I'll leave this for you to read. It's just a little bit more detail about reset pins and things that we haven't already talked about. We don't normally tend to use them in school, so that's why I've just put it in here for completeness, but I don't want to bore you with some of the more details. And if you see, there's the control pin. We haven't spoken about that. So we've got control pin and reset pin. I'll leave you to read about that. Remember, if you can't read this if you're watching online, always pick up the notes as well. The notes are an earlier post within this podcast, so have a look. This is the bit that I really wanted to draw to your attention. It can be shown that T, the time that it's on, is given in seconds by that formula. T equals 1.1 times R1 times C1. And you'll note that it's independent of the supply voltage. Okay, independent of the supply voltage. It depends only on R1 and C1. And I've just said there, look, if R1 is in megohms, which it might well be, and C1 is in microfarads, then T will be in seconds. But that's not to say that you need to put R1 into megohms and C1 into microfarads. You don't. The reason for that is because meg is 10 to the 6 and micro is 10 to the minus 6, so they tend to cancel each other out. But if you put in just the value in ohms, in ohms, and the value in farads, then it'll always give you the right answer. It just so happens that I've said there that megohms and microohms cancel each other out. Okay. Anyway, that's it for now. Remember, as I've already said, pick up the notes on this and follow this along with me if you're not already doing so. The other thing is, I've also set up a Twitter account for Podcast School. So if you sign up, which is free, you can receive text messages that let you know when the podcasts go back on the site. So not only will you get them automatically within your iTunes feed, but you'll also get a message to tell you that there's one ready and waiting to be downloaded. Okay, and you can get that from the More Stuff section. You can get the details from that from the More Stuff section of the website in podcastschool.net. Okay, that's it for now. Until next time then, bye-bye.